Okay, let's get started. There were a lot of technical issues. I had to update my operating system, and then that messed up half the programs on my computer. But I think everything should be alright now. Had to replace my coding IDE, had to replace a lot of things, but I think now we should be up and running and good to go. Alright, let's get started. So, in the last week, we learned a little bit about sliding window problems and how we could use those sliding window problems or the sliding window technique to reduce the running time of algorithms. So for example, in the last problem that we were doing last week with mansions, we learned about how we could replace two for loops with one for loop by simply being clever and dropping and adding certain things. So this technique kind of has a pretty wide application in trying to lower the time complexity of an algorithm. But it turns out that that is not the only way to lower time complexity. Even writing a better algorithm is not just the only way to lower time complexity. And in fact, there's another way, and that is to modify the structure of the data that you're working with. So let me explain that in a little bit more clearly. Let's hope all of this works. Okay, so we're going to talk a bit about sets, maps, and dictionaries today. Sets, maps, and dictionaries. And the first thing I'm going to talk to you about a little bit is the whole idea of a data structure. And we're going to look at a very, very simple example. Okay, so first of all, what is a data structure? A data structure is essentially a way of storing data so that access, search, and other operations are easy. So the operations on a data structure are usually accessing / searching. So for example, when I try and find an element in a list, adding, for example, append in a list, removing, for example, removing an element from a list, and maybe there are other sorts of operations that we will cover soon. So for example, with dictionaries, there might be a certain type of lookup, or for trees, there might be things like comparing and finding the element next to something. There are many, many other sorts of queries. So I'm going to write queries here. So in this case, what I mean is like looking for a particular type of information. Looking for a particular type of information. And the list or array is the most basic form of data structure. And essentially an array, not a Python array, but like a C array essentially, or even a Java array, is essentially one contiguous slab of memory, like this. Okay, it's a contiguous slab. It's a very simple data structure. You can, in this case, you aren't even able to add and remove things very well. You're only able to access, modify, modify the array elements, access them, and declare the size. And that's basically it. Okay, so that's a very, very simple data structure. Now, a Python list is one level higher than this, right? Python list is essentially a dynamic array. It's the dynamic version of an array. And what I mean by that is that it also supports things like adding, which is append, removing, essentially remove, and other things like being able to do slicing, being able to do other things as well. Yeah, so these sorts of things are supported with Python. Okay, so a dynamic array is a more advanced type of data structure than the list, but Python just gives that to you for free, which is great for us. Alright, so now let's look at another data structure, and I want to kind of try to understand, or try to get you to understand, how data structures can kind of reduce our time complexity. And we're going to do a simple example, okay? Actually, I'll introduce one more type of data structure that you might know, which is a Python dictionary. Python dictionary. And it's essentially, it implements associative arrays. What I mean is that with an array you have indices 0, 1, 2, 3, 4, and they're attached to values, right? But in a dictionary, those keys may not be integers. They may be strings, they may be something else. Does that make sense? So Python dictionaries go one level further. They're more advanced. The keys can be anything, first of all. And what I'm going to show you is that lookup in a Python dictionary is optimized. So let me try and explain this. All right. So here's a problem to try and explain this to you. I'll kind of just say it out loud. It's also in the notes. Let's say we want to construct a bibliography for an assignment that's due. Unfortunately, since our bibliography is rather long, we keep forgetting whether I've included a certain reference in a bibliography. So what I'd like you to do is to write a program that checks whether a given hyperlink is in a bibliography. So for example, let's say my input is a file containing n hyperlinks, each of which has length less than 40 characters. Okay? Now I will be given some queries, each of which is a hyperlink. So Q queries after that. Q queries. And what I want you to do is to return yes if that hyperlink is in the bibliography and no otherwise. Does that make sense? So let me write a sample input. So let's say my n equals 2, q equals 4. All right. So my two hyperlinks are google.com and maybe facebook.com, and my 4 queries are something like sydney.edu.au, discordapp.com, twitch.tv, and let's say Google. Okay, so what my output should be just no, 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 and yes, because Google is in our bibliography. Okay, so does the problem make sense? All right, so what is the easy method of doing this? Okay, the easy way to do this the easy method is to store all the hyperlinks in a list. Store all the hyperlinks in a list, and then when we get to the Q queries, what we do is we check the entire list. So for each query, check the entire list to see if hyperlink is in the list. Okay, so how long does this take? So, store all hyperlinks in a list. This takes O of n time because there are n hyperlinks. Now, for each query, there are n queries, and there are q queries, and we have to check the entire list of n elements to see if the hyperlink is in the list. So maybe Google is the last thing that's in the list, and we have to check the entire thing. Or maybe it's not in the list at all, and we have to check every single thing in our list. So this is bad. This takes q times n, which is like O of nq time. So O of n plus O of n times q is just O of n times q, because n times q is much bigger than n. It's really big. It's really, really big. Okay, how can we do better? Is there a way we can do this? There's no way that we'll be able to load all of the elements into memory. No way that we can load all of the entire hyperlinks in the list with less than n steps, because there are n links. We have to process them with n steps. Okay, so we have that O of n factor is still there. So this is still there. Because we have to read every element, we can't get rid of it. But there is something we can get rid of. It turns out that we can get rid of the NQ part if we use what's called a set instead of a list. So using a set. Let me get another page. So using a set instead of a list, we can reduce the running time. So what is a set? So you might have seen in Python that there's this data structure called a set. So we can do something like, instead of L equals just an empty list, we can do something like S equals set. This defines a set data structure in Python. Now there are some really special things about set, okay? Sets and dictionaries are extremely special, and essentially sets are like a very special version of dictionaries, okay? So why are sets special? So first of all, the really special thing about set is that checking that an element is in a set takes constant time. Yes, I'm not kidding you. It's not linear time. For 1 million elements, if I have a million elements and I want to check if some element is in there, this takes like a constant number of steps. It takes a very, very small number of steps. And the reason why is because it's using techniques of hashing and dictionaries and things to essentially map the element to some mathematical function, and it's essentially querying that particular function. So because of the magic of hashing techniques, so I'm just going to write y hashing techniques. Because of the magic of these hashing techniques, the actual membership check, so membership check, so something like if element in set takes O1 time. The other special things about set are add takes a constant time. So this is O1. Remove also takes constant time. This is O1 as well. So deleting an element is O1. With the list, it actually isn't O1. There's a reason, because we have to cast aside all of the other elements in order to get to a particular element in the list, right? But with a set, it actually is O1, because we're using the magic of this hashing technique. I mean, you'll learn a little bit about it when you do Comp 2123 or 2823, the Algorithms and Data Structures course. But essentially, the idea of hashing essentially gets you this constant lookup time, constant adding, and constant removing. Okay, the price of this is that the elements are not ordered. The elements are not ordered, and there are no duplicates. There are no duplicates allowed. Okay, so let's actually do a little bit of experimentation with sets. So let me go into my coding editor. And let's do a little bit of experimentation with how sets work. Okay, so here are some ideas about sets. So let's create a set. So S equals set. And you can actually create it from a list. So you can write, say, 1, 2, 3, 4. And what I can do is, let's say I can write s.add 5, s.remove 3. You can do all sorts of cool things like this. You can add, you can remove, and you can do things like print, hang on, if, say, 2 in s, print true. Okay, this is an idea. So essentially what this will do is that it'll add 5 to this set. It'll remove 3 from this set. Oh, yes, it'll remove 3. So we'll have 1, 2, 4, and 5. And since 2 is inside the set, it'll print true. Fair enough? Okay. Now, another thing you can do, so we've done adding, we've done removing. We can print the length. We can do print len s. And that will give us the length of this, because we now have 1, 2, and 5. So that should give us 3. We can also take unions and intersections of sets. So you might have kind of heard a little bit about this in kind of maths, where you can take unions of sets and intersections of sets. So here's an idea. So let's do, for example, S1 equals set 1, 2, S2 equals set 3, 4. And if I write print S1 dot union S2, I will get the set 1, 2, 3, 4. Okay? I can also do intersections, so print S1 dot intersection S2. Yeah, S1 dot intersection S2, and that will give me nothing because 1, 2, and 3, 4 have no elements in common. That's what the intersection means. Alright, so now we kind of know a little bit about how set works and what its magic property is. Its magic property is that we can now do lookups in constant time, as long as there are no duplicates. Okay. So in our case, with our particular problem about the hyperlinks, we don't really have to worry about duplicates. And the reason why is that if we are given that a bunch of hyperlinks are in there, and we have 2 hyperlinks that are the same, it doesn't matter because they're still inside the set, right? So they're still inside the bibliography. Okay, so what will our algorithm look like? Our algorithm will essentially just be put all hyperlinks in a set, and then for each query, we'll put queries in a list, and then for each query, check if the query is in the set. And the key difference is that this operation here is going to take constant time. The reason it works is because of hashing. This operation takes constant time because of the very special properties of sets and hash tables, okay, and dictionaries. And what that means is that our new time complexity, when we use a set instead of a list, is O of n plus O of n times 1, right? Because it's O of n times O of 1, which is just constant, right? Which is just On. So somehow we reduced our time complexity, by using a set instead of a list. Alright, so this is really good. Lots of other languages implement sets. So for example, in Java, they have an equivalent called the hash set as part of the collections package in java.lang.star. The reason why Java calls it a hash set is because the set is implemented using the data structure called a hash table, which enables the constant time membership check, the adding and removing. And we'll kind of discuss how hash tables or dictionaries work later on, but it's kind of a little bit beyond what we can do now. Okay, so back to the problem. What we do is that once we know if it's in there, we report yes. So report yes if the element is in the set, else report no. Simple enough. The only difference you'll see between the previous algorithm and this algorithm is that we somehow used a set instead of a list, and that enabled us to get a magically new runtime. Okay, this is great. So let's do some practice with this. Let's do a little bit of practice. So here is a problem. Okay, here we go. Let's have a read of it. Thank you for being the scorer for our game of tag. The rules are very simple. There are n people playing today and everyone has a different number between 1 and n inclusive. At the start of the game, player 1 is on the red team, player 2 is on the blue team. All the players start on no team. Over the course of the game, people on a team will tag people who are not on a team. The person who has been tagged then joins the team of the person who tagged them. Note that it is possible that some of the players will not have been tagged at the end of the game. As scorer, we need you to figure out how many people are on each team at the end of the game. Okay, so we have two integers, n and m, the number of players in the game and the number of tags that occurred during the game, respectively. Okay? So in this case, the 8 and 5 represent that there are 8 players in the game, and there are in 5 more lines of input, which means 5 people are getting tagged. Okay? So each line contains two integers a and b. This indicates that player A tags player B, so player B joins player A's team. It is guaranteed that prior to this tag, player A is already on a team and player B is not. Okay, good. Your program must output two integers on one line, the number of players on the red team and the number of players on the blue team. Okay, so let's go through the sample. So we have 8 players, and 5 people are going to get tagged. So number 1 is on the red team, number 2 is on the blue team. So number 2 tags number 7, which means 7 is now on the blue team. 1 tags 8. So 1 tags 8, so 8 is on the red team. 8 tags 4, so 4 is on the red team, and so forth. And at the end of this, the red team has 1, 6, 8, and 4. The blue team has 2, 7, and 5. 3 was never tagged, so is on neither team at the end of the match. Alright, so what are we looking for? This program needs to run in exactly 1 second, or at least at the most 1 second. So what we're looking for is an algorithm that is linear in the number of inputs. Okay, so let's first think of the simplest possible approach for this problem. Alright? So what is the simple way of doing things? The simple way is always to use a list. Okay. Let me video capture. Okay, good. So the simple method is we make two lists. So let's say the red and the blue. We make a list like this. And what we do is we simply we add people to the right teams. So what we're going to do is if we have 2 and 7, so 2 is on the blue team, so 7 is now on the blue team, and we'll put 7 here. Okay? Let's write this a different way. So blue will now be 2 and 7, and red will now be just 1 right now. Okay? Then in the next line, player 1 tags player 8, so we'll get the red is 1, 8, so we'll just append everything to the end of the list, and the blue is still 2, 7. Okay, what about the next line? 8 tags 4. Alright, so the red is now 1, 8, 4. Okay, so do you see the problem with this approach? The problem is that every time you find somebody who's already on a team, so for example, number 8, you don't know whether he's on the red team or whether he's on the blue team. Okay? We don't know whether this number is on the red or the blue team. How do we find that out? Well, it seems like the only way we can find that out is if we go through the entire list. So, what this means is for each query, essentially a tag, we check which team the tagger is on, okay? And if we have lists, this could take a long time. This could take up to O of n operations, where n is the length of the list. So what's the running time of this? We have essentially m queries, each of which is taking O of n time. So the running time, the total running time is O of n times m. The total running time is O of m times n. Okay, so now if we go back to the problem, how big are m and n? How big are they? N is 100,000 and m is about n minus 2. So if n and m are about 100,000, 100,000 squared is 10 to the 5 squared, which is 10 to the 10, which is a huge number. It's much bigger than the magic number we established in the first week of 50 million, which is the number of operations that a computer takes to run in 1 second. Okay, so this algorithm is not going to score full marks. In fact, at the end here, it says if there are at most 1,000 players, we will get 70 marks here. So if you scroll down to the very end, it says for subtask 3, 30 marks, there are at most 1,000 players. So in this case, an O of n times m algorithm, which is 1,000 times 1,000, which is a million, is under 50 million, so we'll score all the marks. But for subtask 4, when no constraints apply, we will not be able to score the marks. Does that make sense? So this requires us to be a little bit more clever. So the solution, as with the bibliography problem, is to use a set. So instead of this, the idea is that we have two sets called red and blue, and we're going to maintain those two sets instead of lists. Let me get my webcam back. So we have two sets called red and blue, which store the members of each team. So what we do now is we use the magic of the set. So what we do is we load everything in. So every time we see a query, so for each, let's just add. So add 1 to team red and add 2 to team blue. Because we're given that 1 is initially on the red team and 2 is initially on the blue team. Okay, so for each query, or for each tag, which is just a query, what they're asking us to do, or what we need to do, is check if tagger in red, and if it is, add the tagged person to the red team. We can also, if that's not true, check if the tagger is in the blue team, and if it is, then add the tagged person to the blue team. Simple, right? All right, let's implement that. So now you guys will get to see how to implement sets in practice and how to use it on a real problem. So this is really similar to the bibliography problem, right? You'll see the same ideas occur again and again in programming contests, and indeed in computer science itself. The set is an extremely important data structure, and the amount of saving that we can use with sets, the amount of saving for membership checks and things like that, is very, very important for a lot of things. For example, we looked at the bibliography example. This might also be useful for things like searching and all of that sort of thing. When you need to search a vast database and you want to check whether something is somewhere, then obviously the set is much more useful than a list in that regard. So you can see that these sorts of ideas are used all through computer science, from search engines to databases and other things. These basic data structures and algorithms. It's not just for contests and stuff like that. Okay, so let's actually implement this. Let me get my VS Code up. This operating system update is rather annoying, but that's okay. I can write the entire program without running it. So let's make our input file. We'll get our input file. Now, what does our input look like? So we have, if I go back to my window capture, if I go back to my problem screen, let me do that. So we have this data, 852718847586. So what we'll do is we'll copy paste this into our input file. I'm copy pasting this. I'm going back to VS Code in this case. And what I'm going to do is I'm going to put it into the input file I have right here. I'm going to paste it in there. Okay, so this should read the input file at the end. So what we've got is nm this map int input file dot readline dot split. So we've read n and m. So for now we'll make our sets. So we'll write red is an empty set, or actually we can put 1 in here, and blue is a set with 2. Note, we could have also done the following. We could have defined red as an empty set and blue as an empty set, and just written something like red.add1 and blue.add2. So essentially what this is doing is we're adding 1 to the red team, adding 2 to the blue team. So now, for I in range m, so essentially for each query, we'll have tagger and tagged this map int input file dot readline dot split. So what that does is it reads each of the 2 separate space separated integers, and we'll write something like this: if tagger in red red.add tagged, if tagger in blue, blue.add tag. Okay, and at the end we just want to print len blue and print len red. Oh, actually we want the red first, don't we? And the length of the red set and the length of the blue set are just how many people are on the red and the blue teams. Does that make sense? It's very, very simple. There's nothing to it. The only innovation that we needed was to use a set instead of a list, because sets guarantee us constant lookup times, and they also allow us to add and remove very quickly too. But the lookup is the main benefit. I can check whether something is in a set like magic with the snap of my fingers, whereas for a list I have to go through the entire list. The disadvantage is that sets do not allow duplicates. But in this case, there is no number that is going to be inside the set twice. Or if it does, that has no meaning, right? You can't be tagged twice, right? So if you see this sort of structure where you have unique elements or no duplicates or something like that, then you should be turning to sets and dictionaries to help you. We'll introduce dictionaries very soon. So let's write the answer to the output file. So n red, so number of red equals len red, number of blue equals length of blue, and then we'll get the output file. Output file dot write. We'll do something simple like string of number of red plus a space plus string of the number of blue, and close all of our files. And that should do it for this problem. Make sense? So let's recap what we did. We read the file. We put 1 in the red set, 2 in the blue set to signify that 1 was on the red team and 2 was on the blue team. Then we added everything to the sets as required, and the main saving was this in operation. And because it's a set, not a list, this is constant time. The add is constant time, just like append. So this is actually just, this is very simple. This is like O of m time. And because m is about the size of n, they're both around about 100,000, this is going to run in time. Okay. So now that we're done with that, I encourage you to code this up in your own time and run it, submit it, do whatever you need to do. There might be a couple of bugs in this code. I haven't run it, but that's the essence of the idea. All right, let's go back for a moment to our paper, and we'll talk a little bit about dictionaries before we finish. Hang on, let me adjust this paper a little bit. There we go, that's much better. Okay, so a dictionary is essentially an amped up version of a set. What it does is it allows you to store key value pairs. So the idea being that we can have something like this. Our dictionary, let's call this dictionary. We can do something like this. Let's say we can have A colon B or C colon D. The idea is that this is a key, and when we look it up, we get the value. So something like dictionary of A gives us D, and dictionary of C gives us D. Why might this be useful? So for example, we might have our keys be names and our values might be addresses. That's one good use of it. So for example, we might have something like the name is like John Smith, and the address is something like 1 Pacific Highway. Whoops, sorry. There we go. All right. So this sort of mapping and key value pairs is very useful. In fact, you see it all the time with phone books and things like that. There are all sorts of uses of this. All right. So here is an example of when you might use this. So let's say we want to filter a stream of incoming tweets. So every time we receive a tweet, we want to check if we care about the author of that particular tweet. All right, so let's say I had something like this. So let's say I have a dictionary of authors. All right, and let's say I had, let's say I was monitoring tweets from Donald Trump. So this would be true, because this is our value. It means we care about this tweet. We might have, I don't know, Obama. True. Scott Morrison. True. And say J.K. Rowling false. Because we know J.K. Rowling just tweets anything she likes, so we can make that false. All right. So essentially, we have some dictionary where a key, which is the person, is mapped to a value, which is whether we care about it. All right. So what we can do is, if we have some strings coming in, let's say I have some queries. Let's say I have a query and it's asking me about, let's say my query is Julie Bishop. My dictionary is going to give me, well, it won't give me anything for Julie Bishop. But for example, if I write J.K. Rowling, it would give us false. For Obama, it would give us true. And for Julie Bishop, it would throw an exception. Because it's not in the dictionary itself. Obviously, we can modify the behavior so things work well. But essentially what we can do is, given a number of tweets, we can check whether we actually care about it or not. So if we have a feed of Twitter things, we have an entire Twitter feed, what we can do is we can search through that feed, and using a program, it can determine whether you actually care about it or not. So this is exactly kind of how Twitter's auto-generated feed actually works. So it looks at who are you following, so that shows which people you actually care about, and if the popular tweet that's there is inside the person that you are or is in the dictionary of the people you are following or the people that you care about, then obviously it will display, otherwise it will not display. So this drastically improves the speed at which you can execute code at scale. Dictionaries, again, the lookup is O1 constant time. Right? It's really, really good. And now we know how to how to initialize it, and how to work with it. So we know how to add. We can also remove using del. You guys should definitely look this up. It's very useful. You can remove things with del. You can add things with the syntax I've given above. And you can search things really simply. You can just write dictionary of key. It will give you the value. And you can do that really, really fast. And I've given some problems in the notes where you can practice how to use dictionaries in order to speed up your runtime. And they look very, very similar to the tag problem. So I really encourage you to go out and try them. So I think that's basically it for today. We learned a lot about sets and how sets can allow you to check if an element is in them in constant time, and how you can use that to speed up the running time of your algorithms without actually doing anything different. We also learned about dictionaries, which are kind of like a key value version of sets, where if you have a key, you can get the values and things like that, and that will really help. So it's like an extended version of the set, and it works on the same mechanism of hashing. So I highly encourage you to try out the problems that I've given in the notes. Definitely look at them. Try and see if you can analyze the runtime of the brute force algorithm, and then what the runtime will be after you use a dictionary or set. Alright, I think we'll stop there, and I will see you guys next week. Thanks very much.